Hello, everyone. Thank you for joining in. Today's Recitation 2, we're going to be talking about predicates and a little bit about some proofs and rules of inference. So let's get started with predicates. I'm going to give you at certain points some time to solve certain questions. If at any moment you have a question or if my voice isn't clear enough, let me know and stop and I'll try to fix it. Okay, so starting with predicates, it's going to be something like this. If we say students like computer science, we can make a predicate like f of x. So if f of x is true, that means x likes computer science. And x can be some variable. X is your variable. It can be some person. So if f of John is true, then that means John likes computer science. If f of Ali is true, then Ali likes computer science. So here we're assuming that x is a student. So with these variables that we're going to be using, they have something called a domain. So what is x? What constitutes as x? What belongs to it? So we're saying it's in this case it's going to be some student. Okay. So before we were working with propositions. So we were saying P can be true or false, and P is a proposition, so it's like some statement. Today is sunny, tomorrow it's gonna rain, and so on. Now we're working with predicates, which is like a function. So it's like a mapping from X to either true or false. Don't worry so much if you don't know what a mapping or what a function is. We'll get to it later in recitations. Right now, just think of it as this x. It's when you plug it into f of x, it's either going to be true or false. So let's translate some of these sentences into English. So we're given the predicate p of x. It means x is a philosophy professor. And L of x, x understands logic. So the domain consists of professors. So x is going to be a professor. For every x, p of x and L of x. So this gets translated into this. Since we say this, it's for every. So this means for every. Or you can read it as for all. It means all the possibilities work. For every professor that we have in our domain, this is going to be true. So P of X means he's a philosophy professor and understands logic. So simply, all professors are philosophy professor and understand logic. So if you're a professor, then you are a philosophy professor and you understand logic. This symbol is read as there exists or there is. When with for every, it was for every possible professor. With there exists, it's at least one. So we're saying there exists at least that these are true, or these predicates are true. So there exists a professor that is a philosophy professor and understands logic. So far, it's pretty simple. Just we're adding the predicates that we have. Okay. What about this? Again, this property is gonna be true for all professors. If this professor is a philosophy professor, then he understands logic. Okay. How will that be? All philosophy professors understand logic. Does that make sense? Before, with the and, we said, hey, you're a philosophy professor and you understand logic. Here we're saying all philosophy professors understand logic. It's kind of like saying, hey, if you're a philosophy professor, then you're going to be understanding logic. Okay? And usually all professors, they are philosophy professors. Like PhD, it stands for Doctorate of Philosophy. So whether you're a computer scientist or an engineer, whatever PhD you do, usually you get referred to as a philosophy professor, other than the actual domain of philosophy. Okay. There exists a professor that understands logic. Simple enough. Okay. Any problems so far? We're just translating from English to, from these predicates into English, and we've introduced two new ideas, which is for every and there exists. And X is your variable. In this case, its domain is professors. Okay. Now, if you remember, this symbol means you're about to try to do this exercise. But first, let me do with you part A, and then you can try to solve part B and part C. So this would be a good point to try and get some papers because we are going to need them today. Translate in two ways each of the following statements into logical expressions using predicates, quantifiers, these are your for every and there exists, logical connectives, or and implication. First, let the domain consist of students in your class, and second, let it consist of all people. So depending on which domain you work on, the translation will be different. So this is going to be for all the parts. Let C of X is a predicate such that X is in my classroom. So if this is true, then X is in my classroom. Two domains. First one, all students in my class. Second one is all people. Okay? So if we're working in the first domain, that means X is just people in your classroom. The other one is just everyone in the world. There is a person in your class who cannot drive. In order to translate these, we have to break down the sentences into predicates. So maybe D of X, X can drive. I'm not sure if in the solution it's actually going to be like this, but usually when we do predicates, we write the positive version. So here, right, they're telling us who cannot drive, but let's do it like D of X, X can drive. And if you want to say he cannot, you'll just say not D of X. Usually it's better to write it in the positive sense, and then you can just use the not logical connective. So, okay, good. That's how we did it. So let D of X be X can drive. So first of all, there exists, so we're only going to be saying this. There is a person in your classroom who cannot drive. So if the domain is just your class, you don't have to specify that he's in your class. We already know in this domain 1, this guy is going to be in your class. So there exists X such that not D of X. There is someone in your classroom who cannot drive. In the other domain, if it's all people, then there exists a person. This person is in your classroom. So C of Y, this person, we just said he is in your classroom, and he cannot drive. So the difference between part 1 and part 2 is in part 2, you'd have to specify that, this person is actually in my classroom. Now, does it make a difference if you use X or Y? No, this is just a variable. You could have said there exists Z, or you could have used X for both of them. Not just because you used X for the first one means you can't use it for the second one. They're two different x's, two different people. Okay? So take a few minutes, try to solve part B and part C. If you have any questions, let me know. I'll be right here.
Third, in part B, the domain is all the class or all the people.
You want to do it for both of them. So this is going to be for all the parts. So you have to do it first if the domain is your class, and then if the domain is all the world.
Okay.
We just do part 1, part B.
I'm going to give you one more minute. If you finished part B, do part C.
Okay. Okay, I'm done.
All right, let's try and see the solution. If you didn't finish it, it's fine. Let's just see if you were kind of close. So, part B. Everyone in your class has a notebook. Well, so we're going to be using n of x. X has a notebook. And just like the x and y, you could have said d of x, a of x. Okay? It's just a letter. It's just a name. So everyone in your classroom has a notebook. So easy enough. It's just for the first one. Just say, hey, for every x, n of x is true. Everyone in my classroom has a notebook. Now, for the second part, if this person is in your classroom, then that means he has a notebook. So here we need an implication. If y is in your classroom, then that means y has a notebook. If you try to do it like this, like c of y and n of y, it's not the same. If you write like for every y this, it's like you're saying everyone in the world is in your classroom and everyone in the world has a notebook. No, you have to say if he or she is in my classroom, then that means they have a notebook. Part C. Somebody in your class is repeating this course. R of x. X is repeating this course. Again, part 1 is easy enough because we don't have to worry about C of x. Just say there exists x, R of x. Part 2, there exists someone such that they are in your class and they are repeating. Okay, good enough. Why didn't we write, for example, C of y implies R of y in this case? Well, here we're saying there is somebody, so there exists at least one person. So these have to be true. It's not like we're saying, hey, if somebody is in your class, then they might be repeating. Because in the first one, in part B, there could be no one in your classroom, and it's still gonna be correct. Hey, if nobody's in your classroom, then hey, everybody in your classroom has a notebook. Whereas here, no, there has to be at least someone there. Okay? Moving on. So, students like computer science. We decided, hey, I'll make an f of x such that x likes computer science. Well, what if I have this quality as well? Students like biology. Well, okay, I'll make another one, g of x likes biology. Okay, then peanuts, and then so on. What happens if I keep getting more and more like qualities? In this case, let's say they're just for subjects. Well, I can't keep writing more and more and more predicates because then it'll never end. We can introduce the idea of a predicate that takes two variables and then does something with them. So you have to ask yourself, hey, should I be using f of x or should I be using f of x, y? With more practice, you'll get an idea of what you want to do. So it'll be something like this. If xy, then that means x likes y. So f of xcs means x likes computer science, x likes biology, x likes peanuts. And you'd still have to specify like what's the domain of x and y. Like could y be anything in this case, or do you want to specify it to a certain quality, like just subjects or food or whatever? Again, with more practice, hopefully you'll get an idea of, hey, should I use this or should I use this? So just 1 minute, look at these and try to translate them, as many as you can. Okay, I'm just gonna throw the answer in your screen because I feel you should be comfortable by this right now. So the first one, there exists x, there exists y, such that p of xy. And and p of xy just means Professor X has taught class Y. Consists of all CMPS professors, so it was specified that X is a CMPS professor. So if X was all the domain and we wanted to specify that X was a CMPS professor, we would have had to create another predicate C of X such that X is a CMPS professor. But we didn't need to do that. So there exists a CMPS professor that taught a CMPS course. There exists there exists a CMPS professor that taught all CMPS courses. All CMPS professors taught a CMPS course. I think here there's a mistake. It should be X and then. Oh, no, this is right. So there exists Y. So there exists a CMPS course that has been taught by all CMPS professors. So C and D are kind of equivalent, right? We just flip the for every Y and there exists X. It's kind of like a trick. So they're the same but different wording. All CMPS professors taught a CMPS course. There exists a CMPS course that has been taught by all CMPS professors. You have E and you have F. Is E wrong? For every Y, there exists X. All CMPS professor has been taught by CMPS professors. I don't know. Let's see. So there exists. So for every Y, all CMPS courses have been taught by some CMPS professor. Yeah, this should be like a CMPS professor since they said there exists X. It's not by all the CMPS professors. Okay, good eyes. Thank you. For every X, for every Y, all CMPS professors taught all CMPS courses. Okay, so this is fine. Okay, good. Moving on. I think this might be the last exercise for these before we move on to predicates. So again, I'll do part A with you, and I'm gonna give you a minute or two to do part B. Express the negation of these. Why are C and D equivalent? Because they mean the same. They mean the same thing. So in C, we're saying all CMPS professors. So we started with for every X. So all CMPS professors taught some course Y. This is part C. In part D, we're saying, hey, there exists a CMPS course that was taught by all CMPS professors. So it's the same thing. If that didn't answer you, let me know. So express the negation of these propositions using quantifiers and in English. So we're given that the domain X is a student in this class. There is a student in this class who had never failed a course. So step one would be to break it down. And yes, let's try and use predicates that take two variables in this case. So S of xy means x failed y. We were already given that x is students in this class, so that domain is specified. We just have to specify the domain of y, which in this case is courses. Translating this sentence is there exists x for every y, not this. Why not this? Because we're saying there exists a student that has never failed a course. So you're saying there exists a student. For all the courses, they didn't fail any one of them. Okay? So not S of xy, you didn't fail this course. So you just have to specify there is a person that for all the courses, they never failed any one of them. What's the negation of this? You just put a big not before it. And when you put the not, the for every and the there exists, they're kind of like switch. So before we had there exists x, now it becomes for every x. We had for every y, it becomes there exists y, and the not just cancels. Since we already had not s of xy, not s of xy will be just s of xy. And it's read as all of the students in this class have failed the course. So for all the students, there is some course where they failed it. And it doesn't have to be the same course. It's just they failed some y. So this y could be different for different students. Okay? Take a minute to solve part B. If there's anything that hasn't been clear so far, let me know, because I think the next idea is going to be on proofs. Okay. Let's check the solution on this. Again, remember, the whole purpose here is you want to find the negation of these propositions. So first, you'd actually have to translate them into predicates and proposition before you can do the negation. So let L of xy be x likes y. Domain of y is majors. So computer science is a major. This is like before. Should I specify the subject or should I specify it as food? And so on. Every student in this class likes computer science. For every x, L of x CMPS. X likes CMPS. We didn't have to specify that x is in this class because remember, the domain of x is students in this class. Negation, just add a not. For every x, it becomes there exists x, not L of x CMPS. There exists a student. There exists, a student or some students. It's at least one student in this class who does not like or who hates CMPS. Okay? Any problem?
دكتور
Yeah.
ليش ما حطينا كمبيوتر ساينس مثلا هي سي اوف اكس وحطيناها بدل ال اوف اكس وكما سي ام بي اس هي ذات
Can you repeat, like, why didn't we say C of x such that x is CMPS? Is that your question?
لا قصدي انه ليش اذا عملنا انه define C of X هي الكمبيوتر ساينس
Okay.
حطيناها بدل ال of X كما سي ام بي اس.
So what you want to say for every x?
هو قصده انه يعمل السي اكس انه لايك كمبيوتر ساينس وانه اذا حطيناه جوا يصير every student like computer science. So always true.
So just tell me, how would I write the statement?
هيك مثل ما انت كتبتها.
Just like this? Okay. Well, first of all, x is a student. Okay. So if you say C of x, the definition is x is CMPS, this statement is just saying every student is CMPS. So it's kind of like saying every student is of their major is CMPS, which is not necessarily true. Okay. So step one, we needed the predicate to be two variables, x likes y. Just to say that all the students will like y, and y is some major. So this CMPS, it's not a variable, it's just a constant, an instance, just computer science.
Yes.
Okay.
Okay, thank you.
Welcome. Before we actually move on, this was bothering me, and I think C and D, they're not actually equivalent. Like the positioning of which quantifier you use first makes it different. So in part C, we're saying for every x, there exists y. So all CMPS professors taught a CMPS course. It could be a different course. Like you could have Professor 1 taught CMPS 209, and you have another professor that taught CMPS 211. This is just saying that all the professors have taught some course. This is part C. Part D is saying, no, there exists some course that was taught by all the CMPS professors. So for example, CMPS 211 was taught by Professor 1, Professor 2, and whatever number of professors you have. Okay, so they might look the same, but they're actually different. So thank you, Ahmad, for letting me look at this again. There's something I didn't understand in 6a. What was it you didn't understand, Samer? In the negation. Okay. Why isn't it? Because we're saying there exists y. Like there is a course. At least a course. So you could have said all students in this class have failed at least one course or have failed a course. Okay. So if it had been for every y, then it would have been, hey, all students in this class have failed all the courses. Okay. So this translation is actually important, whether it should be plural or not. Okay. And is everything clear here for part C and D? New proofs. So determine whether this and this are logically equivalent. Just gonna maximize it, same thing. So we have to see if this is equivalent to this. And what does equivalence mean? It just means whenever this is true, this is gonna be true. And whenever this is false, this is gonna be false. I'm gonna solve this for you since it's the first proof idea. And just to give you a heads up, no, it's not gonna be true. Like this is not logically equivalent to the other one. So what should we do when the case is not? Well, you have to find some example, some counter example, where the first one is true and the second one is false, or vice versa. The first one is false and the second one is true. That way, we'd prove they're not logically equivalent. Okay, so focus with me here on just trying to understand it. Don't worry about trying to come up with the proof on your own. So step one is gonna be this. We're gonna assume that P of X is a proposition that is sometimes true and sometimes false. And Q of X is some proposition that is always false. So again, P of X, sometimes true, sometimes false. Q of X, always false. For example, this is enough. Like you could use this abstract idea to try to prove that, oh, now they're not equivalent. But I'm gonna give something a little bit more concrete. So for example, let's say it's this. P of X, B, X is greater than 5,000. q of x, x is less than 0. Your domain is going to be integers greater than or equal to 0. Greater than or equal to 0. So your domain is just going to be n. If you don't know what n is, it's just 0, 1, 2, 3, just the positive integers. For example, if I tell you p of 20, this is going to be false because 20 is not greater than 5,000. If I tell you p of 5,001, it's going to be true. It is greater than 5,000. If I tell you p of 1 million, it's also going to be true. So we can see that sometimes p is going to be false, sometimes p is going to be true. Q is always going to be false because q of x is x such that it's less than 0, like strictly less than 0. But my domain is 0 and above. So whatever value of x you choose, it's always going to be false. So q of 0, false. Of 1, also false, and so on. You get the idea. Okay, great. So we came up with p of x that's sometimes true, sometimes false, and we came up with q that is always false. But how does that solve the problem? Well, what's the value of this according to p and q? For every x, if p of x, then q of x. This is saying if p of x is greater than 5,000, so if x is greater than 5,000, then x is less than 0, which is obviously false, right? So in a little bit more detail, since p can sometimes be true and sometimes can be false, and q is always false, so false. Remember, implication is only false if we have true implies false. So we're asking ourselves, for every x, is this whole thing true? No, because what combinations do we have? Either p of x is going to be false and q of x is going to be false, so f implies f, which is true, or p of x is going to be true and q of x is going to be false, which is false. So not for every x, this whole statement is going to be true. Again, not for every x, this is going to be true. So this whole thing is just one big false. Okay, stay with me, stay with me. What about this side? For every x, p of x implies for every x, q of x. This part, is this true? Is every x in my domain greater than 5,000? Again, no, because, for example, 20 makes it false. So this statement is asking you, is every x greater than 5,000? No. Sometimes yes, sometimes no. But this means that the whole statement is false. What about this part? Without thinking, you should just directly say false, because we created q of x in this way. For every x, is it less than 0? No. For every x, it's greater than 0. So this is also always going to be false. False implies false means this whole thing is one big true. So we were able to come up with a case or with a counterexample such that the left side became false and the right side became true. So with a counterexample, okay? And if I just said with a false implies false and true implies true, you could have said it with just these two. This is a little bit extra to try to imagine it better. Any problem with this part? Can we use the truth tables with quantifiers? I'm not sure, but I don't think so. Because before, when you only had like P, Q, R, P can only be true or false. But here with P of X, it can be true or false, but depending on X. And what could X be? It could be infinitely many possibilities. So I'm not quite sure, but maybe ask your professor. That's a good question. Probably not. Okay, any other questions? Okay. Okay. If you only got like half of it, that's good. When you watch it again, it'll be even better. If you have any questions, please let me know. So not equivalent because we found a counterexample. One way of doing proofs is counterexample. Okay. It's a little bit easier here. Take a look at this, and okay, actually, before we start this, if you wanted to translate this into English words, we're just trying to see, hey, can this for every x be like split here and split here? Like, can I do that and remove the brackets? The answer was no. Now, here we're saying you have for every x f of x, and there exists x L of x. Can you bring this guy over here and open these brackets? And it becomes there exists y. Without actually like trying to give me a proof, does this make sense or not? Like, should this be true? Okay, so we have one yes. And that yes is correct. Because these two x's are different. They're not the same x. Like, okay, we started for every x, then we reached and, so it's kind of like this x stops here. This is only where it exists. Now here we started with a completely different x. Even though they have the same name, as variables, they're different. There exists x, L of x. So when it's like this, yeah, you can use the same symbol. But when it becomes here in brackets, you have to differentiate between this x and this one, or this variable and this variable. So we say for every x, there exists y, such that this. How to actually prove it? Well, this is equivalence. They're asking for equivalence. So you have to start from the left side and try to reach the right side, and vice versa. Start from the right side and reach the left side. So for example, for every x f of x, this is kind of like saying you x1. Now x1 is an arbitrary x1 for any x. And there exists x, L of x. So it's like L of x 2. Okay? This is the whole existential thing you took in class. But the difference here, x1, it could be any x. But x2 is for some specific x, so for some specific value. Now, this x, we take it to the left. So for every x, open the brackets, f of x and L of x2. Then for x2, for every x, for every y, f of x and L of y. Okay. This is proving it from left to right. It's simple enough. I trust you can do from right to left on your own. So instead you start here. So if I want to do like the first step, it becomes there exists y, f of x1, and L of y. Then step 2, f of x1 and L of x2. And it could be A3 or C. It's just arbitrary. And you keep going. So this is like the actual proof of how to do it. So there's understanding what the question is trying to tell you, and there's actually doing the proof. Okay? Any problem? Part B. Any idea? Like, is it also true? So the only difference between part A and part B is these guys. The answer is yes. They're also equivalent. By doing the same steps as before, you get the same result. The only difference, this is for ands and this is for ors. I see this as just trying to understand that this x is different than this x. And you can use any variables. This is the point of these two parts. Part B. Part C. I'm going to give you a hint. Part C is false. They're not equivalent. But can anybody tell me why? We cannot use De Morgan. I'm not sure here if, okay, like how I understand De Morgan, you have not A and B, you get not A or not B. So here I don't see De Morgan in terms of not becoming or any flipping. How I see it is, it's like they're taking this for every x in common and saying the other thing. So can we like take this for every x in common? In part 1, they're saying for every x f of x is equivalent to for every x L of x. So this means for every x that makes f of x true, it also makes L of x true. And for every x that makes it false, it makes the other one false. So this is this part, the second part. So it's saying for every x, these two things have the same value. So true when true, false when false. What's the first one saying? It's saying that the whole statement is equivalent to this whole statement. It kind of looks similar to the whole 5,000 and positive integers, right? The first one is false, right? The question says, are they equivalent? So is the left part and the right, like this whole thing, is it equal to this whole thing? But you're saying that the first one is false. Can you find an example which makes the whole first one, so this whole thing, true, and makes this whole thing false? Because when they say, hey, for every x, these two are equivalent, doesn't really give you that much of a confidence. Like, I'm pretty sure you can come up with a zillion predicates or propositions where they're not equivalent for every x. So, if you can find another example on your own, that's great. But I was trying to think something that has to do with the normal numbers that we know, something like even and odd. Okay, so assume that f of x is telling you x is even, and L of x is telling you that x is odd. Let's check the right side. For every x, f of x is equivalent to L of x. This is definitely false because, hey, you're saying for every x being odd is equivalent to x being even, which is wrong. You're either odd or even. So whenever x is actually even, it's going to be true for f of x, but false for L of x because it's not odd, and vice versa. So for the right side, it becomes false because, hey, it's not true. What about the left side? For every x f of x, this is false. Not every x is going to be even. Some are going to be odd, some are going to be even, so this makes it false. Same for every x L of x. Not every x is going to be odd, some even, some odd, so it's also false. So they're equivalent. This whole thing is false, this whole thing is false. False is equivalent to false, there you go, it's going to be true. So we came up with a counterexample that made the left side true and the right side false. You could have made another example which makes the left side false and the right side true. That's also fine. Okay. It's new, I know, but you will get used to it. It's 6 o'clock, but all of you were late for 5 minutes. So I'm going to keep going with the idea of inference. If you need to leave, that's fine. I think I need like 10 or maybe 15 more minutes. So yeah, then I'll upload it and you can watch it if you need to leave now. Okay, so inference. Rules of inference. An example is hypothetical syllogism. So it's a bunch of hard to pronounce rules that we're going to be using. So P implies Q and Q implies R. The way I like to see this specific rule, it's kind of like we're building a bridge. You get to do this. Skip. So if P implies Q and then Q implies something, then P can also imply that something. So with inference rules, you're given that this is true and this is true. Okay? What does that mean? Well, P and Q can be anything except true and false. And same for Q and R, they can be anything except true and false. Because true and false would make the implication false. So with inference rules, you're given a bunch of premises, a bunch of hypotheses, and you try, and there's an and between them, and you try to conclude something. So in this case, for some reason we're not going to dive into now, if you have P implies Q and Q implies R, then you can just get P implies R. And it's actually not that difficult, right? It's like you have not, P implies Q is just not P or Q. And you have not Q or R. So you can distribute these or do whatever, and you're going to reach a point that is not P or R, which is P implies R. Okay? If you'd like to do the work on your own, this is the proof or step. We also have a bunch of other different rules. I'm going to go over them as just a little bit. So if I have P implies Q is true, and I have P is true, then Q has to be true. Because we're saying, hey, P is true. So Q can't be false, or the whole thing will be false. So the only option for Q is to be true. Modus tollens, same thing, but we're saying, hey, Q is false. Since not Q is true, that means Q is false. The only thing P can be is true. Is false. So the whole thing can be true. Thus not P is false. Sorry, not P is true. Okay, we already saw this. Just build the skip. Simplification. Both P and Q are true. So you can get Q. Or you can get P. Like both of them are true. Addition. You know that P is true. hey, add whatever you want to it. Add P again. It's still gonna be true. Disjunctive syllogism. You have P or Q, and you know that P is false. So you get Q. Like, this is true. You know that P is false, just remove it. Conjunction. Two things are true. Their and is also true. Kind of like the opposite of simplification. Resolution. Not P or R, P or Q. Why do I get Q or R? Well, P can either be true or false, right? Let's assume that P is true. So this is going to be false. This is going to be true. Since this whole thing is true, then R has to be true. So it's equivalent to saying Q or R. Or if it was the other way around, if this was false, then this would have to be true. Then Q also has to be true. So in any case, in any possibility, either Q or R have to be true. Okay, maybe a little bit much too time on this part. How can we actually make use of this stuff? Show that the argument from a form with these premises, do this. So we're given these premises. I want to reach this. They're comma separated, just so it's easier. You can assume like you have ands between them. Like they're all true at the same time. I want to reach Q implies R. So how we actually solve this, we want to write the steps and the reason. Like the reason you write each step. After doing a bunch of these steps, we hopefully want to reach some step that says they're false. Some step that reaches Q implies R, which means we're done. So from what I see, I want to reach Q implies R. I have Q here. It implies something. So I want to start from there and try to see if I can reach R. Well, I see that Q implies U. And I have here that U implies P. And then I have that P implies R or S. So that's kind of like the map I'm trying to build. Question. We know that if I had Q implies U, and I have here given that U implies P, I can build the bridge, which means that Q implies P. And I can venture on here and try to find a solution. But can I conclude, since I have Q implies U and T, since I have this, can I get this? Yes. What's Q implies U and T? It's just not Q or U and T. If I distribute this, not Q and U, not Q or U, and not Q or T. This is just Q implies U, and I have Q implies T. And there's an and between them, so you can use, where are you? Simplification. Two propositions. If you have an and between them, you can use either the left or the right. So in this case, it's useful for me to get Q implies U. So how do we write this? Hey, I have Q implies U and T. This is a premise. I can conclude Q implies U by, what's the rule called? Simplification of 1. Because 1 is equivalent to these two guys, you can just simplify and get the part that you want, which is Q implies U. Since this is a big jump from 1 to 2, it would be nice to further explain it. Like you can say, since this. Okay. Let's keep going. If you're confused of how we should be thinking like this, with practice it'll become easier. Right now, just see if you're on the same, see how we can do it. So is anybody lost right now? I can repeat if somebody's confused. So like we're way past the recitation time, so thank you if you're still here. If you need to go, that's fine. I'll upload this. So okay. Well, I'm just gonna continue with my map that I built. So I said Q is gonna go here to U, and U goes somewhere, which is P, and P is gonna reach R, which is what I want. So I keep going. U implies P. That's a premise. So I can use the bridge idea, which is hypothetical syllogism. So step 4 says, I have now Q implies P by 2 and 3 HB. Okay, cool. Now, where does P take me? Well, P takes me to R or S. And I really only want the R. I don't want the S. How can I get rid of it? Well, I have not S. Not S is true, which means that S is false. So ideally, I'd like to remove this S. It's not necessary. Like R or S is just gonna give me R since S is false. But I can't just say this right away. So step 5, I'll just write it. P implies R or S. We know, by the way, that or is stronger than implication. So the brackets aren't necessary, but it's nice to have them to better understand it. So this is a premise. P implies R or S. I also have not S. It's also a premise. I'm gonna conclude, I can't write here. I'm gonna conclude that I actually do have this. P implies R. 5 and 6 simplification. Why do I have this? Well, what's P implies R or S? It's just not P or R or S. And I also have not S. Going back to the rules, where are you? This. P or Q, and you have not P, you get Q. We have not P or R and S. We also have not S, so we can conclude not P or R, which is just P implies R. This isn't actually simplification. It's disjunctive syllogism. ES. Oh. Can anybody tell me the last step? So we only have step 8 and it's done. We just have to, okay, so I have P implies R, and where are you? Q implies P. Are these enough to solve the problem? Yeah, it is. Why, Cheryl? Because using HP, you can get Q implies R, 4 and 7, just building the bridge between them. Okay, so that's it. That's it for this. Any problem? Okay. Okay, so take a few minutes to try to solve this. Okay, so this is how we do it. Same idea, it's all about trying to find a train of thought or a mapping. So we want to reach that H is true. Well, the only place I can find H in my premises is here. So before, in this example, oh damn, in this example, I started from Q, then I went somewhere to U, then from U I went to P, then from P I went somewhere. Here, it's kind of like doing backtracking. I start from H, but I want to backtrack. So H, I get there from T. Then I have T here. I get to T from not W. I don't have not W, but I have W here with S. So this is where I should start. Well, almost here. Since I have an S here, and I have these guys, not S and C. Actually, let me try to write it. Maybe it will be easier then. So step and reason. Step 1, we have not S and C. This is my premise. Step 2 is just not S, simplification of 1. So even if I have no idea what I should be doing right now, I know that I want to use W implies S. And I have here not S and C. So I know that these guys have to work together. So you can think of them as like Lego pieces, even if you have no idea just how to use them yet, try to get them. So I have not S, and now I can write the premise, W implies S. And what's the rule? Oh, going all the way back. So I have not S and an implication. Well, before actually trying to look at the rule, not S is true, which implies that S is false. But W implies S is true. So the only thing that I can conclude here is that W has to be false for the whole thing to be true. So this is a premise. I can conclude that not W is true. But I just need to get the name of the rule, which is, I think it's this one. Modus tollens. Yeah, it's this one. This is your S. This is your W. You have not S. So you can conclude that you have not W. Okay. Modus tollens of 2 and 3. Or 5. Again, with my Lego pieces, I have not W, and here I have not W implies T. I'm literally just not thinking. I'm plugging them in so I don't waste time if this was an exam, and I'll see what happens. So not W implies T. This is saying that not W is true. So T has to be true for the whole thing to be true. So I can write away that it's not, sorry, it's just T. And I can go to my sheet if this was an open book exam, and I'll get the rule name is modus ponens. So modus ponens of 4 and 5. Keep going. Step 7 says I have T implies H. Premise or hypotheses or rule, whatever. I can conclude, finally, I just have H because modus ponens of 6 and 7. Is that right? Yeah. So T is true. So H has to be true. That's how I conclude it. And that's that for this part. Okay. Moving on. Exercise 7. Assume we have the hypotheses, the stuff. Use rules of inference to show that the above implies this conclusion. So same as before, but now we're given a bunch of English sentences. And there's I think like 3 ways we can approach this. Step 1, or way 1, we can try to use like the normal propositions that we know. Like we can say, hey, P means the first sentence. Khalil works hard. That could be the first sentence. And then you make Q and so on, and it'll look exactly like what we were doing here. Or step 2, or way 2, would be using predicates. So it would be like, hey, P of X means X works hard. And you can conclude, or you can say at a certain point that you have P of K such that K is Khalil. So this means Khalil works hard. And you do the same for the rest. So for example, D of X, X is dull. And we have, so this is like P of K implies D of K. If D of K, then he will not get a job. So same as before, I like to write the positive. So X gets the job, and if you need to use the negation, you just write it. So J of X, actually D of K implies not J of K. So if Khalil is a dull boy, then he does not get the job. Okay. So, this is just P of K. Well, if you want to use the rules of inference here, it's like just 3 quick steps to reach Khalil will not get a job, which is not J of K. This is the conclusion we want to reach. Well, you have this, let's call it 1, and you have 2. 1 and 2 are gonna give you 3, which is d of k. What was it called? Mode exponents, I think. Okay, so mode exponents. Part 4, you'll get not, or actually, let's say 4 is this premise. So d of k implies not j of k. 5 will get you not j of k because 3 and 4, again, mode exponents. Okay, so quick way to reach the conclusion. The third way you could have done this is just reading the English. Like you could have said, hey, Khalil works hard. We have this given, like it's true, and we have this given. So we can conclude the mode exponents of these two, that Khalil is a dull boy. And then Khalil is a dull boy, and you have this, so you can conclude that he will not get the job, like just like directly saying it because it's in English. But I wanted to give a taste of actually using predicates because of these 4 ideas. So universal, instantiation, and generalization, and same for existential. So this is just saying if you have for every p of x, if you have this, you can conclude that there is something that makes it true, and c could be anything. Or vice versa, if you have p of c and c is anything, you can conclude that for every x p of x, for every x p of x. Existential is the same thing, but you're saying there exists x, and when you say c, it's like for a specific instance. This c could be anything, arbitrary, we use arbitrary. This c is specific, it's an instance. Okay. So when we were solving, what problem was this? When we were solving this problem, we were kind of using the UI, UG, EI, EG. We were either using all of them or some of them. Like when we say this step gets me this. So for every x f of x, we said f of x1, and we said L of x2. Here we were using UI. We were universally instantiating x1. And here we were universally, again, instantiating, sorry, not universally, existentially x2. Since x2 is an instance and x1 is a general. Yeah, so that was the instantiation. And then when I said, hey, I want to go backwards and say for every x, f of x and L of x2, this was the generalization. And then when we said, again, for every x, there exists y, it's also generalizing. So for every x and L of y. And I think that's everything. Okay, so yeah, that's everything. So we've been recording for an hour and a half. I really need to tone down the recitation because it should be only an hour. Okay, so that's everything. If you have any question, you can use the forum, you can send me a message and let me know. Samer, Lean, are you? Oh, hi, Lean. Oh, you're still here with me? I want to memorize your names in case I ever want to give you guys bonuses for staying with me for an hour and a half. Okay, thank you guys for staying with me for an hour and a half. I'll try to make it just an hour next time. Okay. See you Monday, I think. Bye-bye. And hey, for everyone that's watching this recording, if you actually manage to reach this spot, let me know. I might give you a bonus as well for sticking it this far. Good job. And I hope you got everything that we said. Okay. See you next time.